Hello, hello, hello. This is chapter 13, first part of the homework with that, which deals with density and pressure at depth. It does not deal with flowing fluids. But I want to go over the solutions with that. Please make sure you make corrections and show your work clearly for corrections. Basically, you've got something which is a sphere, and it says that the density of air in there is 1.4 kilograms per cubic meter, which is a little high for normal air, but not unreasonable. And it says if the radius is halved, then what would happen to the density? Well, the formula for volume of a sphere is 4/3 pi r cubed. So if you make the radius 1/2, then the volume would be 1/8. 1/2 cubed is equal to 1/8. So if you have 1/8 the volume, you would actually have 8 times the density. You would actually also have 8 times the pressure, assuming that the temperature stayed the same, which it may or may not. So therefore, 8 times 1.4 is 11.2 kilograms per cubic meter. This one is about this James Cameron sphere. This is actually a pretty cool one. It is an immense amount of force, like literally hundreds of millions of newtons of force on something that is only 1.1 meters in diameter, which tells you how strong things have to be. So the depth of this submersible sphere was 11,000 meters. And to find the inward force on it, we need the absolute pressure and the surface area. So told us the diameter is 1.1 meters, so I quickly made that radius 0.55 meters. Surface area of a sphere, 4 pi r squared. So that got me 3.8 square meters of surface area. The pressure is atmospheric pressure plus rho GH. Well, this atmospheric pressure isn't going to mean much. That's basically the same as 10 meters. But I added it anyhow. And it's ocean water, so that density is 1,030 kilograms per cubic meter. I used 10 newtons per kilogram. If you use 9.8, you'd be a little bit different, but that's fine. And so I ended up getting the absolute pressure at depth was 1.143 times 10 to the 8th pascals. Well, when I multiplied that by the surface area, I got 4.34 times 10 to the 8th newtons. So again, 400 million newtons. That might not make sense because it just seems ridiculous, but that's the truth. So pressure is a pretty big deal. The Earth's gravitational pull on all that water, pretty big deal. For problem 15, you had a U-shaped tube. I should have drawn this, and then it basically had a gas. It was asking about the pressure in the gas. So on the left side, the tube was 10 centimeters taller of mercury, and the density of mercury was given in a table earlier in the chapter as 13,600 kilograms per cubic meter. I used 9.8 newtons per kilogram here. 10 extra centimeters on the left. Well, that pressure plus the pressure of the gas would equal the atmospheric pressure on the right. So that ends up being around 88,000 pascals, 88 kilopascals of pressure in the gas. P21, basically you had a boat with 3 meters times 20 meters, and it was sitting 8.8 meters deep in salt water. I was asking you how deep it would end up being in fresh water. Well, fresh water is less dense, so hopefully you realize it would have to push aside more volume. Therefore, it would be 0.824 meters deep. How did I figure that out? Well, I used the volume times the density of the ocean water to figure out the mass of the ocean water displaced. That therefore has to be the same as the mass of the boat. So I could have multiplied everything by 9.8, but no need to do that. In fresh water, we have to still displace 49,440 kilograms of water, but the density is less. So that density times length times width, times depth would have to equal the mass of the boat. So it's going to be 82 or 0.824 meters deep. Basically, this is 3% less dense, so this is 3% deeper. 23, you had a block of 10 by 10 by 10 centimeters, so that's 0.001 cubic meters. Notice, again, I'm converting it into standard units right away. And it was wood with the density that was given, so that's 0.7 kilograms of wood. And if the water was fresh, then if its density is 70% that of water, then 70% will be below the water line and 30% will be above, so 3.0 centimeters above the water line. If it's salt water, then A smaller percentage will be below the water line, 67.9%, so 32.1% would be above the water line, so it's 3.21 centimeters above the water line. 24 is kind of neat. I wanted to assign this problem, and I think there might be one later on I also assigned like this, which deal with figuring out buoyant force of a balloon or something like that, because we're going to do a lab in class. So, we've got 5,700 cubic meters of volume and for the helium, and it says that the mass of the gondola and the envelope and so forth is 4,300 kilograms. So the lifting force is equal to the difference in densities times the volume times G. So if you don't multiply by G, then you can find out the essential amount of mass that would be lifted. So it just depends on whether things are asking for force or mass, and here it asks for mass. So density of air, 1.2 kilograms per cubic meter. Density of helium, 0.166 kilograms per cubic meter. This amount times, so this difference in densities times that volume would give us the net amount that we could lift. But the mass of the ship itself is 4,300 kilograms, so it could only lift about 1,590 kilograms of cargo. For problem 25, which is the last one, we've got this thing on a string. It's 100 cubic centimeters of aluminum. It's an ethyl alcohol. So I looked up the density of ethyl alcohol earlier in the chapter. It was 790 kilograms per cubic meter. Density of aluminum, 2,700 kilograms per cubic meter. So similar to the problem here with this balloon, except we're dealing with liquids and solids as opposed to two gases. So essentially in this case, if we had, I should have drawn a free body diagram. We have zero net force, so the tension and the buoyant force up would equal the gravitational force acting down. So the first thing I'm going to want to do is find the volume of aluminum in cubic meters. I said it was 100 cubic centimeters, but I need to convert that to cubic meters, and notice I did that in a fairly specific way. We have to take into account all three dimensions of the block. So I could have done 0.1 times 0.1 times 0.1 as well. Oh no, I couldn't do that. It gave me this volume, so I had to do the conversions, basically 0.01 times 0.01 times 0.01 times this volume. So next I have to find an equation with the variables that I want. So I know that the force up equals the force down. Tension plus buoyant force is equal to gravitational force. To find the mass of the block, by the way, if I now have the volume of the block, I need to multiply the density of aluminum times the volume of the block. That tells me that the mass of the aluminum block is 0.27 kilograms. That's going to help me figure out the gravitational force. So tension plus density of the liquid times volume of the block times 9.8, that's rho VG, will give me the buoyant force. Why the volume of the block? Because it's completely submerged. If the block was somewhat above water or partially above water, I would have to use the volume of the liquid displaced. But here, because it's completely submerged, the volume of the block is equal to the volume of the liquid displaced. So this would be my buoyant force, and then mg would be my gravitational force. So we get T plus about 0.77 newtons is equal to about 2.65 newtons. So I have the tension is going to be 1.87 newtons. And again, you could use the difference in densities times V times G, in this case, to figure out the tension. So density of the block minus density of ethanol. That's similar to how I said we could do things up here. So I hope that helps, and we'll do part 2 next.